friends and students, welcome to all. For today's session, thin and thick cylinder. What do you mean by cylinder? In general, cylinder is a mechanical device used for storing, receiving and processing the fluid. In engineering drawing, engineering graphics, you have many times constructed cylinder and you are aware of this. But this cylinder may have a open end or closed end, and based on that, cylinder may be pressure vessel, storage vessel, pipe or a engine cylinder. Thick and thin cylinder forms the basis for pressure vessel. And pressure vessel, what is the difference between pressure vessel and cylinder? In pressure vessel, it is also a closed container used for holding gases and liquids at pressure above the ambient pressure. And design of this pressure vessel and manufacturing of the pressure vessel, which is regulated by some of the national and international bodies. That's why while designing and manufacturing it, we have to follow national and international codes. Cylinders or cylindrical pressure vessels classified into two types. One is thin and thick cylinder. When to say it's a thin cylinder and when to say it's a thick cylinder. Let us consider it's a open end cylinder which is cut into two parts, but this inside diameter is di and having wall thickness, this wall thickness, this is t, di and t. If this the ratio of di and t is greater than 15, then we can say it's a thin cylinder. And if ratio of di and t is less or equal to 15, we can say it's a thick cylinder. Here in thin cylinder, generally we will find boiler cells, pipes or tubes. And in thick cylinder, high pressure pipes and gun barrels are the example of thick cylinder. Let us see how to find out the stresses in thick and thin cylinder. Now first one, thin cylinder. Now this is cylinder having inside diameter di, having wall thickness t, subjected to internal pressure pi. This thin cylinder in general is subjected to, or three stresses are going to induce in it. One is circumferential or a hoop. It is also known as tangential stress denoted by sigma t. Another stress, that is longitudinal stress, which is along the transverse section in this fashion. And third one is the radial stress. Third one is the radial stress. But for in thin cylinder, it is subjected to circumferential and longitudinal, and magnitude of this radial stress is very, very less. That's why this is neglected in the analysis. Now let us see here the half portion of this cylinder. Now here when it is cut, here you will get the circumferential stress. Now di is the inside diameter, pi is the internal pressure, t is the wall thickness and sigma t circumferential stresses along this L. Therefore, by considering the equilibrium of these forces, the pi into di into L is equal to sigma t into 2tl. So you will get sigma t is equal to pi into di by 2t. This is the expression for circumferential stress. And if we are going to consider longitudinal stress, the longitudinal means, now here you have to cut the cylinder here and you will get the stresses along the axial direction. Look at this diagram. Along the axial, this is sigma L, pi and di and wall thickness t. For this, again equilibrium of forces, pi into pi by 4 into di square here is equal to sigma L this into pi, so along the circumference into di and into wall thickness. So you will get sigma L is equal to Pi into Di by 4T. And this is very, very negligible. That's why we are not going to consider that these two stresses are going to induce in thin cylinder. But looking to these two expressions, you will find the magnitude of sigma T is more than the sigma L, or 2 times more. Look at these terms, 2 times more. Therefore, we can make some remarks. Circumferential stress is twice the longitudinal stress. And we can modify this expression to find out the wall thickness. The T is equal to Pi Di upon 2 into sigma allowable. Instead of writing sigma T here, sigma allowable is written. That is permissible stress based on SYT upon FUS, based on the material used for the cylinder. But if longitudinal and circumferential joints are considered here for the thin cylinder, then this expression is multiplied by your efficiency of that joint, efficiency of circumferential or longitudinal. And accordingly, we are going to modify this expression Pi into Di upon 2 into sigma allowable or permissible into this efficiency, which is in fractions. And generally, if you don't know, the 0.85 is the value that we have to consider. Again, second thing here, in case of thin cylinder, you will find the magnitude of the circumferential stress is the twice of the longitudinal. So what is going to happen here? When this stress or circumferential stress exceeds the yield stress, that time cylinder is going to fail in circumferentially, and if longitudinal stress exceeds the yield stress, it is going to fail along the axis or in transverse direction. That is the important thing. But looking to this magnitude, while designing it, we have to use this expression Pi into Di upon 2 into sigma allowable or permissible. Now let us see the stresses in thin spherical vessel. We have seen cylindrical, now spherical. This spherical vessel is divided into 2 parts, and you will find here at this section in parts, it is subjected to sigma T only. Considering the equilibrium of forces for this half part, so what you will get here, circumferential or hoop stress Pi into pi by 4 into Di square into this sigma T into Di into T. As usual expression, we can find out sigma T is equal to Pi into Di 4T. That means for thin cylinder, you will get this. We can find out sigma T. And if the joints are considered, then it is multiplied by your efficiency to find out the wall thickness of the thin spherical vessels here. And the capacity of the spherical vessel or volume is given by pi by 6 into Di raised to cube. Now let us consider thick cylinder. Now we are in this, when to say it's a thick, when Di by T ratio is less or equal to 15. And generally you will find the examples of high pressure pipes or gun barrels. Now let us consider, this is a thick cylinder, inside diameter is Di, outer diameter is Do, having wall thickness T and inside pressure, that is Pi. Now to make this analysis, consider a small elemental ring here, this ring having thickness Dr, and this ring is shown here. It is subjected to some of these forces or stresses, you can say. Now here this is sigma T, circumferential stress. This is R is the radius, or 2R is the diameter here inside. Then subjected to sigma R also. In thick cylinder compared with thin, the magnitude of sigma R is more. That's why we have to consider this stress also, along with sigma T and longitudinal stress. But longitudinal stress is uniform, or sigma L is uniform. Now here, this is R, then sigma R, then this is Dr is the elemental ring, and this sigma R plus this del sigma R the stress. Now here, what we have to do, considering the equilibrium of the vertical forces acting on half part of this ring, sigma t acting towards this side, then this sigma r plus del sigma r. So what we have to do, let us consider the equilibrium of vertical forces. This is sigma t and this dr and this dr, the 2 sigma t dr plus this sigma r plus del sigma r, which is acting here to us outside, into 2 here, this r and this dr, the 2 in bracket r plus dr is equal to, now here this sigma r, which is in opposite direction, into this r means 2r inside. So that's why sigma r into 2r. This is the expression. Now solve this expression, or multiplying by the sigma r to this 2r, sigma r to del r, then del sigma r to r, and this. Solving it, you will get this expression. After simplifying it, neglect del sigma r and del r dr here from this expression, and making the arrangement at the last, you will get this expression a sigma t plus sigma r plus r del by del r sigma r is equal to 0, equation number 1. But it is assumed that in this analysis longitudinal stress is constant over the cylinder wall thickness, and according to distortion or strain energy theory, the longitudinal strain epsilon 1 is given by the 3 principal stresses sigma 1, sigma 2, sigma 3, here sigma L, sigma T and sigma R. And where we use the Poisson's ratio is modulus of elasticity, and this is longitudinal stress. These 3 terms are constants. We can making the arrangement of this longitudinal strain, the sigma R minus sigma T is equal to this. From this equation, arranging this equation, you will get this. Here E, mu and epsilon, the strain along this or longitudinal strain, which is also constant. Therefore, this term is constant. The sigma R minus sigma T is equal to, this term is constant. So we have assumed here this constant is equal to minus 2c1. Minus 2c1, to make the expression or this derivation simple, or analysis of this derivation simple, it is assumed minus 2c1 is a constant. Now subtract this equation B or equation A from equation B. So what you will get? This term you will get. Again multiplying by both the sides by R, so you will get this expression, that is expression C. Then this term R square into del by del R into sigma R, derivation or differentiation of U into V. Solve it, then substitute here and again simplify it, so you will get this expression. And then by integrating, what you will get? These terms in terms of constant C1 and C2, or arranging these terms, you will get sigma R is equal to minus C1 plus C2 by R square, equation A. This is for sigma R, and sigma C1 and C2 are the constants. Then from equation E, substituting the E in equation B, again you will get sigma T in terms of C1 and C2. This is another expression F. That means from E and F we can find out sigma R and sigma T in terms of C1 and C2. But C1 and C2 are constants, that we have to find out. How to find out it? By using boundary conditions. At the inner surface, R is equal to di by 2. The sigma R is equal to pi. By substituting this boundary condition and another condition, at the outer surface, R is equal to dV by 2, sigma R radial stress is equal to 0. By using these two boundary conditions, we can find out C1 and C2 here. This is C1 and C2 from equation E and equation F. After finding this, what we have to do? We have to substitute the value of this C1 and value of C2 in equation G and equation F to find out sigma T and to find out here sigma R. And after that you will get, substituting the value of C1 and C2, you will get sigma R is equal to, now here in this case negative sign is used because this sigma R, the compressive stress in this expression, which is used here, negative sign, and sigma T is equal to plus pi di square upon dO square minus di square bracket complete dO square upon 4r square plus 1 bracket complete. That means by using this expression we can find out sigma R and sigma T. But here at the inner surface and outer surface, the value of this radius and inner radius and outer radius and the value of pi or sigma R is going to change. Therefore, we can find out here, look at this. This is inner surface, this is outer surface. In this case, you will get the sigma R, which is maximum at the inner surface, but it is going to decrease and become 0 at the outer surface. Then second, the sigma T, which is maximum at the inner surface and which is going to decrease, having some magnitude at the outer surface. Therefore, what we have to do? We have to find out the value of sigma R and sigma T at the inner surface and at the outer surface. Now consider at the inner surface. At the inner surface, but R is equal to di by 2. And therefore, substitute the value of this R is equal to di by 2 in the expression of sigma T, and sigma R is equal to minus pi. Negative sign already we have used. In the expression you can substitute here. So you will get these values. So we will get sigma R is equal to minus pi at the inner surface and sigma T is equal to this expression. Similarly, we can find out at the outer surface R is equal to dO by 2, and substituting this value dO by 2 in this expression and in this expression, what you will get, sigma R is equal to 0 and sigma 2 is equal to this expression. These equations are applicable at the inner and the outer surfaces of the thick cylinder. Now, we have considered the longitudinal stress is uniform. How to find out this longitudinal stress, that is sigma L for the thick cylinder? Considering the forces in axial direction, look at this. This is sigma L. This is sigma L. And already we have calculated it for the thin cylinder also. Same method we can apply by equilibrium of the forces. Pi into pi by 4 di square is equal to sigma L pi by 4. But here thick cylinder, the inside diameter and outside diameter that we have to consider. Therefore, area is going to change. It's like a hollow cylinder. Pi by 4 in dO square minus di square. So therefore, sigma L, you will get this. And this is applicable to both the cases. So therefore, based on this analysis, we can say circumferential stress at the inner surface we can calculate by this expression. Circumferential stress at the outer surface by using this expression. In this expression, we have considered that is dO by 2 at the R. Radial stress sigma R is equal to minus pi at the inner surface and is equal to 0 at the outer surface. And longitudinal stress magnitude, which is constant or uniform in both the cases, at the inner and at the outer surface. By using this expression, we can find out the stresses in thick cylinder. But in data box or design box, main number of equations are available to find out the wall thickness of thick cylinder. These equations depends on the materials used for the cylinders, whether it's a brittle material, whether it's a ductile material. Based on that, different material equations are available. But here, when material is brittle, generally Lamage equation is prepared. When material is ductile, that time Bernoulli's equation or Clarivinot's equation is applicable when cylinders with closed ends, and Bernoulli's equation is applicable when open cylinders are made of ductile material. In next session, we will see Lamage equation, Clarovinus equation and Bernoulli's equation for brittle and ductile material. Thank you. I have referred V. Bandari's book for this presentation. If you have any query, you can contact me 9890426679 or pbkushare@kkvak.edu.